All right, we'll go ahead and get started. Welcome everybody who's just joining online. This is another one of our Human Factors in Aerospace webinars from the Aerospace Technical Group for HFES. This is a pretty special one for me because the folks here who are presenting today are from the company that I work for, Beta Technologies. And so this has been a few months in the making, and we're excited to be sharing some of that good work and interesting human factors work that we're doing with the technical group. As always, I'm Rodrigo Rose. I'm part of the Human Factors and Ergonomic Society Aerospace Technical Group leadership team, and I run this webinar series. So if any of you are interested in participating in a webinar in the future, you can always reach out to me, or if you know anybody who you think would be interested, please reach out to me, and we'd be happy to put you on our platform. I will now turn it over to the rest of my teammates here to introduce themselves, and then we'll get started with the presentation.
Okay, well, there's two Tylers, so I'll just go first as the first Tyler. I lead the ALIA training team here, previously an RQ-4 Global Hawk drone pilot, and our team makes all of the curriculum and manuals to train the pilots and maintainers how to make the aircraft that we make here at Beta Technologies.
I'm Adam Lowe, and I'm on the training team as well, and I focus on pilot development for our new fleet of vehicles. Most of my background is in military rotary wing before coming to Beta.
My name is also Tyler. I lead the human factors team here at Beta. I'm also a flight instructor and a LEA pilot, so have that really good interaction between flying the aircraft and helping with the design and evaluation for pilots.
And I guess I've introduced myself earlier, but here at Beta, I'm a system safety engineer, and I kind of form the bridge between the system safety and human factors teams at the company. So let me go ahead and share our slides. See how we'll do this. Let me know if everybody can see our slides.
Yeah, all good.
Great. So today our presentation is going to be titled Beta's Technologies Evaluating Novel Systems Through Traditional Human Factors. And what we want to talk about here is how we're developing our novel aircraft and integrating human factors methods and tools to evaluate the systems that don't really have much precedent in the categories of aircraft that we're developing. So just a little bit of background on Beta. We are an electric aircraft company. We make battery-powered next-generation aircraft, and I'll talk a little bit later on about the types of aircraft that we're developing. But we also develop charging infrastructure for these aircraft, as well as training programs that include curriculums and immersive simulators to train pilots and mechanics to fly and operate these new and novel aircraft that we're developing. What we're going to focus on in this presentation is going to be kind of at the intersection of the first and the third bullet on this screen. How we integrate our training programs and our human factors evaluations of electric aircraft, particularly with focus on those novel aspects of that. The two aircraft that we are developing currently at Beta are the ALIA VTOL and the ALIA CTOL. The VTOL, as the name suggests, is an electric vertical takeoff and landing aircraft, and the CTOL is a conventional takeoff and landing aircraft that's suited for airport-to-airport missions. Our focus for this presentation is going to be on the CTOL aircraft. And that aircraft, though it falls into a Part 23, which is your conventional general aviation aircraft category, it has quite a few new and novel technologies incorporated into it, like electric propulsion, high voltage battery powered flight, fly-by-wire flight controls, and all of those come with new challenges for how do we display that information to pilots, how do we assess the effectiveness of our aircraft and of our systems from a human factors perspective. And that's a little bit of what we're going to be talking about here. We're going to be focusing primarily on the energy management side. So the kind of middle part of this slide that you're seeing here with our batteries and how we communicate that information. But before that, I think it's important to talk about the certification framework that we have and that we're working with. And so I'm going to turn it over to Tyler Prather to talk about that.
Yeah, so we here at Beta are certifying a Part 23 aircraft, so normal category airplanes with 19 or fewer seats and a maximum takeoff weight of 19,000 pounds or less. Just kind of a certification 101 high level overview. So I won't get too deep into the weeds of this, but just to have a general understanding. Since we are a US based company, we are certifying through the FAA. And ultimately looking for a type certificate. So this design meets the FAA requirements and is safe to fly. So compliance with the Part 23 regulations ensures a safe and certifiable design. And with that, we have quite a few human factors related regulations for all of the pilot interfaces. So ensuring that you're providing the correct information to the pilot, and then it meets within this framework for a safe and user-friendly aircraft. Go to the next slide. So for historically, there have been very prescriptive requirements. So Part 23 tells you, the designs that you need, and they're pretty prescriptive historically. But with advancing new and novel technologies, Part 23 has been restructured for performance-based regulations. So this allows for more flexibility of designs, innovation, and certifying new and novel designs. So as an example, some of the historical regulations talk a lot about fuel gauging and how that is presented to pilots. But when you kind of break the mold and go into electric aviation, how do we certify our new designs that don't quite align with historical aircraft? So the safety outcome remains the same with Part 23 Amendment 64. Ultimately, we're looking for a safe and usable aircraft that is pilot friendly. So Amendment 64, like I said, rewrites those prescriptive requirements more so as safety objectives and kind of takes the high level perspective. Then you go into detailed design standards. So the applicant, which is Beta, will propose design standards that act as those prescriptive standards. So these can come from MIL standards, ASTMs, or some of those historical regulations. Those are then accepted by the FAA as means of compliance. And then once that point NDDSs are accepted, the certification program is identical to historical Part 23 programs. As an example, one of the larger human factors regulations is 23-2600, which covers the flight crew interface. So again, just using this as an example, these are high-level safety objectives versus very prescriptive requirements. So ultimately, we want to ensure that the pilot view allows them to perform their duties without any excessive concentration, skill, alertness, or fatigue. So having the regulations in this way allows us to kind of mold what designs we're creating and what interfaces we're providing to the pilot. And then again, this is just a visual provided by the FAA that kind of shows the difference. So like I said, Part 23 Amendment 64 now has the performance-based objectives and rules, and then you come up with the prescriptive requirements, and then from there on, the traditional means of compliance are the same, versus Amendment 63, where the standards and the rules are those requirements. And then this is just another example of the differences, or the rule language, and then how you elect to comply by more of that prescriptive requirements, which will kind of come up to that safety objective. All right, and I'll hand it over to Adam.
So one of the unique, nuanced, really fun parts of the job here at Beta that brings the four of us and many others together is the opportunity to support flight test and human factors evaluations by providing some training internally to Beta employees that are going to be performing various duties in those activities. And so before Tyler goes in a room with someone to do a human factors evaluation in the simulator, for example, we'll make sure they have the baseline knowledge they need to understand the aircraft and its systems. Part of that involves exposing them to some, depending on their background, new ideas that really aren't common in aerospace already. Depending on their background with ground vehicles and other tools and things out there, they may have no awareness at all. And so this slide is one of the key ones that we really run into pretty quickly, which is the concept that our aircraft don't require any fuel as their energy source. And so fuel is simply an energy source. It's obviously the most common one currently used in aerospace. And we're hoping to change that. Part of that then is exposing them to some of the differences here. And so the biggest one that folks first think of is that there isn't a change in CG or a change in weight as you use this energy source. Electrons are moving, but there's nothing getting consumed, and there's no, obviously, to our benefit from a sustainability aspect, there's no emissions from the vehicle. And so that does change the way the pilot interfaces with the system. Something like pounds of fuel is no longer relevant in this conversation. And so this baseline awareness of the differences in how we provide energy to the aircraft, not with fuel, but with electrical energy stored in batteries, is one of the first nuanced differences. That then begs the question, how do I see this and how do I interface with it in the flight deck? If I don't need to keep track of fuel or anything like that, what do I need to keep track of? And that presented us as Beta Technologies with an opportunity here to look for a novel way to present that information. So when we look at what that opportunity is, we decided that really the best and most intuitive way to approach this would be to take terms that pilots already know and they already do some pilot math with, and just give them new terms that allow them to do the same math at the same time. And so previously, when they're used to using gallons and gallons per hour or pounds and pounds per hour to determine their time of flight, we can look at two different terms that provide the same math architecture, which is kilowatt hours and kilowatts. And so depending on how much you've seen these in the past, they're a bit of a misnomer sometimes when you look at them, but kilowatt hours is a unit of measurement equivalent to gallons. It's the amount of things you have, it's stored energy. And the kilowatts is the rate at which you're using that. The two often get confused just because kilowatt hours includes a time-based term in there, but that is your quantity. And then kilowatt hours is how fast you're using it. And so using the example there, a pilot's used to looking at a gallon of fuel, or 450 in this case, and saying, okay, I'm using 150 per hour, and I've got 450 in the tank. I can get 3 hours of flight time off of this aircraft with that fuel. And our aircraft, the goal was to provide a display and provide a user interface that allowed for that same quick reference, and the pilot's background knowledge of how to do that math is the same. They just have a different term to use. And this makes it much more achievable for a pilot to come into a conversation like this with very little background understanding and really very little need from a systems understanding to really know the differences in a battery versus a fuel tank and still operate the vehicle safely. And so this was a key design consideration we made. And so the next question is, how do we want to display this to a pilot? There are a lot of different ways that different people have approached this. One of them was through the concept of percentages of state of charge, right? We use this in phones a lot of times. My iPhone right here in front of me has got a percent right now. I'm on 76% for the day, which isn't bad by noon, right? And so that means I know I can probably make it through a full day using 76% state of charge on my phone. But this phone is relatively new, and in 2 years' time, that 76% at 11:30 in the morning is not going to last me the whole day. But how long is it going to last me? Then it becomes a question I've got to answer through experience and assumptions, a lot of things that really aren't easily done without some really, really intuitive knowledge of the system and without an incredibly large amount of risk that I have to assume. And so knowing when my phone's going to die is relatively low risk. Knowing when my plane's going to run out of energy is considerably higher risk. And so what we decided on then was if we want to move away from something like a simple percentage that doesn't really tell the full story, and we want to then use things that allow pilots to just change the terms and do the same math, a display like this, which is shown on the slide, is how we think we can get after the same solution with a different way. And so you've got energy as a display there on the right side, the blue blocks. Each of those blocks represents a single battery pack in our system. So each of those is a high voltage pack, together collectively providing, in this case, 225 kilowatt hours of energy at a full charge. And then conversely, the power gauge, just to the front left of it, is an arc display, and that shows you your current power being used. And so that's your consumption. And so with the voltage times the current, I can determine what that power is. And that's my current use of my high voltage system. 394 kilowatts, as the example shows. And then I can compare that to the energy I currently have available to me in my tank, so to speak, which is 225 kilowatt hours, which is just that power multiplied by the time. And so I could do 225 kilowatt hours worth of work. And I can see right now that I'm above 225 kilowatts of current use. I'm nearly at 400. And so I'm nearly doubling the amount of time that I have, the amount of energy that I'm using compared to what's in the tank, right? And so if I was to use 550 or 400 as the reference point here, I know that I'm not going to get quite a full hour out of the tank. And we won't touch on temperatures for today, but just to note that this is our always on displays for the pilot for their battery system. And so from an electrical standpoint, this is what they always see. And Tyler will talk about this more later, but I'll just reference it now as kind of a teaser for comparing this to other aircraft you may have flown or be exposed to. A lot of other aircraft, simple ones, may have a simple dial indicator that shows fuel flow. More advanced aircraft systems will have an FMS that allows you to compute really accurately your fuel flow, but it's typically not part of your always visible display that's right in the pilot's primary flight of view that they're expected to reference, and that is intended to provide really usable information at any given point of time in flight. That is sort of a difference we've chosen to take with this, and part of it is because of the opportunities and challenges that lie within electric aircraft. And so this is what the pilot will always see with terms that are new, but are able to be interchangeably used with things like pounds or gallons of fuel as they currently do. And with that, I'll turn it over to Tyler to talk about some of the other opportunities and challenges out there.
Yeah, thanks, Adam. When we think about electrochemically stored energy as opposed to fuel, we end up with a unique design constraint or a unique pilot understanding challenge. Traditionally, with combustion, every drop of fuel, if you have access to it, has the same explosivity, has the same ability to produce power for a system, regardless of how much fuel there is. As long as you can access it, you've got full function available. And so in traditional combustion applications, when you can no longer access it at given attitudes or power settings, you hack a line into the certification of an aircraft at a single unusable. And you say there are moments in flight based on attitude or power settings where we can't reliably rely on fuel getting to the engine. And thus we will say that that is zero for mission planning purposes. And it's a relatively clean and regulatorily understood parameter. As we move into a new energy source in electrochemically stored battery energy, the power capability of a battery pack is a function of the energy state of that pack. And so now you can see the y-axis in a battery is much more dynamic and reducing at different gradients throughout the discharge of a battery pack. This allows for a ability for us to hack a line at a known capability, but potentially also hack other lines at other known energy states where we could, and we've successfully had some initial conversations, define multiple different performance levels of our aircraft based on the power capability of a battery pack, where you could have an unusable at the full capability of an aircraft, and then define a minimum usable capability of a propulsion system, like the ability to maintain cruise at altitude, for example. Or I know Todd in the emergency technology has a watch party right now. When we start thinking about additional capabilities of battery electric aircraft, for example, VTOL applications, there may be as many as 4 lines in an aircraft that is capable of conventional and vertical takeoff and landing, where you have full performance of all the installed power plants, a minimum thrust-borne performance that we promise based on the battery's energy state, a full performance of conventional operation, and then finally a minimum acceptable performance of conventional operation, all of which could be defined as usable for different phases of flight and are functions of the amount of power available in a battery. That's why instead of having simply a flow meter, we have to have a gauge, because we're really asking pilots to cross-reference multiple different things when they're looking at this gauge and intuitively understand what they could have if they were to ask for something different. For example, as you can see on the large arc, there is a green tick and a green arc within it that can reduce down in our power gauge depending on the energy state of an aircraft. If an aircraft is in a low energy state, for example, the gauge that you see on the right-hand side blown up shows a reduction in the power capability of the battery. If the systems installed were able to request that much power, that would be the limit of power available. And so we offer to the pilot as a reference to known usable amounts of power. For the CTOL application, you can see that there is a TOGA reference line and a cruise reference line for takeoff and go around, and for a max gross takeoff weight 14,000 foot cruise power application. That would be at about 150 kilowatts and about 400 kilowatts respectively. And that allows pilots to understand what could be available based on the state of energy of a battery, what they're actively using, and if they were to change the power demand of their engine, to know where the fuel allegory, power capability, and flow rate of power would be referenced or cross-referenced after that power demand. This separation of power and energy allows us a very linear energy presentation. So you have a non-linear and ever dynamic power capability, and separating that out allows a very linear energy capability as long as it's ticking down to a known usable energy. For us, we set 0 at the minimum usable energy, which is a cruise demand of power in today's design, at 150 kilowatts of potential power. There is still power below that, but we don't call that usable for any phase of flight. And so 225 kilowatt hours is a promise that regardless of your flow rate, when it ticks down to 0, you're going to have a linear correlation to the flow rate and the energy that can be done with a simple algorithm or a calculator, the same way pilots have always done, and can even be plugged into mission planning tools like ForeFlight to allow them to mission plan the same way they've always been trained to do. This allows us to place a reference line linearly at 30 minutes at a predetermined power setting, where you see there's 30 minutes remaining at normal cruise in the yellow line that you see to the right side of the energy gauge. And finally, the gauge reaches the bottom at 0 usable energy, even though there are still electric capability in the battery pack below that. Tyler, there's a storyboard that the other Tyler is going to go through here to talk about what a pilot is looking at as they are in different phases of flight.
Yeah, and so as Tyler and Adam were saying, when you have this non-linear kind of power reduction toward the end of your energy capability, it is different than a typical fuel and piston aircraft, where once you have no fuel remaining, your engine cuts off. And because we don't have that, how do we show the pilot, hey, you're running low on fuel and you're losing capability of the aircraft potentially if you continue. So on the left-hand side, you see that you have full energy and you have that green indication you have all the power capability that you could want. Then we've elected to have a 30-minute remaining. So when your energy reaches that yellow bar, you'll get a yellow indication, and then that green capability shows that you still have full go-around capability, full power capability, but it is walking back. And so in these cases, you can visually monitor and show that if you had a full TOGA power setting, you would run out of energy a little bit faster. And because we elected to still show the numerical values, you can see that at 150 kilowatt hours and 75, if you do that quick mental math, you have 30 minutes. So those numbers modulate with how much power you're pulling, and you can do that quick understanding. And so if you need more than 30 minutes, you would pull your power back and maybe go into a descent, or potentially have to modulate your power. Going into that 10 minutes, you can see that green line is still ticking back, but you still have full power capability. But at that cruise setting, you only have around 10 minutes. Then for the last 2 slides, when you get into a point where ideally you're not in these, the pilot's never actually seeing these in flight unless there's a true really low energy condition. But we have looked at these where now at the 5-minute remaining mark, if you have cruise power, you cannot have go-around power, or you have the capability to do it, that one time that you need it, and after that capability is going to walk down and you're going to take that energy. And then at 0 fuel remaining, you have the red 0 energy and the red kilowatt hours. And so like Tyler said, this is where you no longer have that cruise power setting, but there will still be energy going and your engine may still be operating, just not at that optimal power setting. So again, these are situations that a pilot would ideally not be seeing, but because we have that limitation there where there's differences in aircraft capabilities, we have to show it to the pilot in a way that makes sense for them. And then moving on to our last slide, kind of bringing it back to traditional human factors approaches. So because we have plenty of new and novel technologies in this aircraft, how do we say any pilot can fly this aircraft and we make it simple and intuitive enough in these flight deck designs? So a lot of work went into, typical task and error analyses to determine what is a conventional pilot looking at? What information and what mental math are they doing throughout the flight? What are you monitoring? How are you determining that you have X amount of time left in your flight and you'll land with X amount of fuel? So as we've kind of shown in the decisions that we've made is pilots are constantly monitoring their intended fuel flow or intended fuel consumption based on what they're actually getting and what their actual fuel gauges say. We're doing the same thing here just with energy, so that math is the same. And a very conscious choice that Beta Technologies chose to enact based on pilot experience and those analyses. We also spend a lot of time in the simulator. So these are some pictures of our full simulator that we have here at Beta. The training team uses this resource as well as the human factors team, and we take a lot of information back and forth based on specific structured human factors evaluations, but also some of our training. So our training team will have pilots that, don't understand concepts, or maybe here are some points that we struggled on, and that kind of iterative design process feeds back into the design, and we can make sure that we streamline it for the future of aviation. And then, like I said, the certification, once you get to the point of having that certification basis, the process is merely identical to a piston or typical Part 23 aircraft, where we do all of the analyses and all of the certification and compliance showing, as well as simulator and flight testing.
So thank you, Tyler, and Adam, for the talk. I'll now open to any questions. Do we have any questions from anybody in the audience? If not, I can ask some questions. Put these guys on the spot.
Hi guys, this is Josh. Haven't talked to you in a while, so nice to see you again.
Hey, Josh.
I do have a question on slide 17, just for clarity, regarding the cruise and the go around. Are those equated to a prop RPM? The toga and the cruise lines?
No, Josh, they're specifically equated to the performance of the engine. And so the toga performance promises that when you ask for 100% torque of the engine, that you're going to get 100% torque of the engine. And the cruise reference is similarly a cruise demand of power at 150 kilowatts. But there is an RPM that is viewable to the pilot on the engine gauge, but that is altitude dependent. If you're at a higher altitude, you're going to get a faster IPM at a different torque setting. But the pilot sets and cross-references torque only.
Okay, gotcha. So is it kind of like an N1 setting or a fan setting on a turbine engine that it moves, but it's just based on engine performance? Is that what it is?
I think that's a good way of thinking about it. The engine performance, the amount of torque that you can make is not altitude dependent. But because of the air density that changes based on altitude, you'll get a higher RPM at higher altitudes than you will at lower.
Awesome. Hey, thanks guys. Great job on the presentation.
Thanks, Josh. Good to see you.
Anybody else online?
Do you want hand raise or just call out? What's best?
I think you can just call out a question if you have one.
Yeah. Great presentation. Thanks for sharing. One of the numbers that's really important to me as a pilot in modern avionics is a number fuel over destination, right? I know if I got 45 gallons, I have a smile. If I have 30, I'm kind of frowny, Do you have sort of the same thing, kilowatts over destination? And I assume that meaning becomes the same to a pilot, if so? Thanks.
Yeah, yeah, it's exactly the same kind of math. If when you do your pre-flight planning, you're looking at, okay, I'm intending to do 140 kilowatt hours at my cruise power setting. And like we were saying, kind of that math is the same. I use, for flight to determine that. And then you kind of have that reserve setting. So some of the numbers that you're using the same kind of math and having that, okay, I want to land with 60 kilowatts or whatever it may be. For that flight planning.
I think a really interesting thing that we've noticed over the years at Beta, both with our own aircraft and operating other aircraft that are out there, both fuel and battery powered, is we're really able to combat a lot of an inherent concern about range anxiety by using a number like kilowatt hours, because it allows them to do have the same familiarity with the aircraft performance capabilities using a known number that is equivalent to like a gallon or a pound of fuel. It is admittedly a smaller tank than they're used to in a comparative fuel aircraft, because you can just get way more efficiency out of, or way more combustion and way more energy and power out of a fuel source than you can out of a battery. But it essentially is the same conversation, and they just need to do the math on how many kilowatt hours do I need for this given route. And then if I get in the aircraft and I've got more than that number of kilowatt hours, or if I'm looking at my screen dynamically and my kilowatt hours over my destination are above what I planned for, they're able to do the same pilot math and have that same conversation internally on that. So for folks that come from a vehicle background where some of them, they're used to like a percent state of charge and they know that 40% is about what they need to get home at night. That is really hard to trust when you are in the air and know that 40% needs to work. And so I think that's how we've been able to do that. And a shout out to Garmin, because you all have been, great partners in this effort that we've been taking with how we display some of these things to pilots. One of the developments that's been coming along with the Garmin G3000 Prime is that performance planning, and how do you do that with an electric vehicle? And that's been a really awesome development to see be undertaken.
Thanks.
Great presentation. Thank you very much, guys. So I have a question regarding alerts and notifications. So if something were to go wrong, for example, a thermal runway or a battery pack is getting hot, like is at a higher temperature, what you guys are considering in terms of how would you notify the pilot about any anomaly that might be going in the electrical system?
Yeah. Hi, Boomin. Nice to see you, by the way. We have a integrated crew alerting system within our system. It's not shown on any of these displays, but we do have a crew alerting system window in the pilot's primary field of view that follows a standard 1322, so warnings, cautions, and advisories schema. Also, we use first limit indications on the temperature gauges, so you have that constant understanding of temperature and readout and the ranges at which they go from like a caution to a warning. Anytime that you go up into that caution range, you're in that yellow range. We have a little yellow or amber indication and then a CAS that's associated. So we have a lot of systems within our aircraft for in-flight monitoring, and all of that is tied into a central alerting system.
Okay, thank you. And just a quick follow-up question. So the display schemas that you have presented in the presentation, are they similar for the VTOL variant of ALIA, or is it different from the conventional model?
Yeah, Boomin, I think one of the things that's really important, we get this question a lot when we show the power gauge that you see here on this storyboard, because if you're only looking at CX300 or looking at the airplane variant, you'd ask yourself why you're showing all of this inaccessible power. And Josh and Tom know that Beta have been working really hard to try to maintain as much commonality between both of our aircraft, because frankly, our Part 23 airplane certification is attempting to prove out and establish as much precedence as possible in pilot interface as well as operational usability of the novel presentations that we've been developing with human factors. This is an example of a gauge that's intended to transcend from both conventional operation to vertical takeoff and land operation, and potentially even beyond, where in a VTOL application, all we would do is add additional reference lines to the power gauge at higher power capabilities based on what full performance of all 5 engines in our VTOL would be, or the minimum acceptable performance for a thrust-borne landing would be. And so a pilot would be able to have a very quick in their peripheral cross-check of the power capability of an aircraft at a given state of charge or a state of energy. And we believe that there's a lot of good reason to not have an ever-changing presentation depending on what variant of our platform you're in.
Got it. Thank you very much.
And that does carry through, but just it's a great question. That carries through to a lot of the physical interface too. The control architecture of the aircraft is identical between the two, with the exception of the lever that sits between the 2 pilot stations is fixed for CX-300, and it moves sort of like a collective position does on a helicopter for the vertical takeoff and landing vehicle. So as much as we can keep things synonymous between the 2 vehicle types, so that a pilot familiar with one is also inherently familiar with the other, we've done that as well with the design.
I'd like to ask one question of you all because embarrassingly, I am the only non-pilot in this room. 3 of them are pilots, and you all at some point had to transition from being trained on and learning to fly a fuel aircraft to learning to fly and train people on an electric aircraft. How has your experience as pilots helped you kind of get a better understanding of what would need to be communicated, of how you would like to train this, and were there things that particularly stood out to you when you first got into this field that then you were able to transfer into kind of your work?
Can I tell a beta story about the Pipistrel? Yeah. So the first electric certified aircraft is a light sport aircraft. It's the Pipistrel Velis, and we love it. We have 5 of them. It's a really great trainer. It's a really great experience builder. But one of the things that we did, because we wanted to operationalize electric as much as we could, to learn as much as we could, it's a culture that we have here, was we would ferry ourselves from Burlington to Plattsburgh. And we're all insatiably curious. And so we would do these essentially system challenges where we'd say, okay, I'm going to take off, you're going to take off. We're going to literally fly in formation with each other to Plattsburgh, doing the exact same profile with 100% state of charge in both vehicles and a different state of health, where one battery is a year old and another battery is 2 years old, for example. And we'll say, what do we land with from a percent state of charge perspective when we get to the other side? And what we found is there were times where we would go from Burlington to Plattsburgh, and one aircraft would have 70% state of charge, and the other aircraft would have 50% state of charge. And that became a relatively common thing that we would have to reinforce when people were taking an aircraft. Was you have to ensure you have to go check the secondary page for the state of health. You have to cross-reference tabular data to make sure that you know what the potential range would be. And it's one of the reasons why kilowatt hours was so important to us. That a pilot, to go back to Bill's question, for example, a pilot would be able to say, hey, I know with reserve on this day that I need 180 kilowatt hours or 180 beans. And regardless of how old or cold that battery is, I know with an estimation error, it's going to give me at least 180. And if it doesn't, I know I can't take the aircraft. And that provides you a lot of surety that what you're doing is going to operationally work. And so I think flying what you build as a culture here has enabled us to pull some of those into the operational design of the aircraft.
You know what, if I could tack on to that, it's an interesting thing that what is that tolerance? For example, in the plane that I fly, it has a fuel flow gauge. And we do everything by fuel flow, and that's what our fuel over destination is. And that fuel over destination will often say, as I said, 40 gallons. Then we'll land, and for this aircraft, the limitation on the fuel gauges is they're only accurate when you're on the ground, stopped in a level area, which is kind of weird, but that's how it's certified. And so that fuel flow is accurate. It is accurate. But when we land, we'll say 40 gallons, then we'll go and check what the tanks are, and the tanks might be 32 gallons. Or sometimes be on the other side, 45 gallons. So maybe that's an interesting certification argument at some point to say, hey, we're well within the tolerances of what fuel gauges are today on Part 23 aircraft. I don't know if that has come up in your discussions, but perhaps it's helpful if you understand what I mean.
Yeah, it certainly has. It's also particularly why we found a lot of value by having that indication for us in the primary field of view, where it is a reference that we want the pilot to use, as opposed to in a lot of aircraft, it's like a useful tool, but you really shouldn't or probably can't always rely on it in certain instances. But really with electrical batteries architecture, the ability to really tell down to the individual kilowatt hour accurately whether or not it exists or whether or not it's usable is much easier to do with our system, provided it does put a lot of the onus on us as the OEM to make sure that the calculations that are going on behind that screen are accurate to provide the pilot the best knowledge of their systems. I was going to say to your question, Rodrigo, I think what my piloting background and experience both before and at Beta has helped and has influenced some of the ideas here with our vehicle is I came primarily from a crewed aircraft background, and most of my solo flying really came either my own time and predominantly now through Beta. And I think a lot of my flight deck interface was from the context of I at least have one other pilot, if not other crew members there to support me, and certain design changes that I probably wouldn't, or design decisions I probably wouldn't have made if I was building the plane or the helicopter that they made and certified, were sort of suboptimal. And the way that you got around it was with a crewed environment where you said, hey, I really can't get to that screen easily, or I can't calculate this quickly. I'm outside flying. Can you do this thing for me? And that provided for some great conversation and ability to train people on how to use the systems better, but it did have a lot of inherent limitations that really made it feel like you needed the crew to operate the plane. Fast forward then to flying a lot more single pilot here at Beta in various aircraft. You run into the same kind of conversation, but there's not someone there to help you. And so you really focus in on what's the most efficient flow to use or the most efficient way to do this and use the system. And you sort of have to load shed on things that don't really work that great in a single pilot environment. So I think taking both those backgrounds into something like this, where we have two pilot stations by design, because we want to provide for that in-aircraft training capability that is kind of already common to the culture of flying. But making sure that the things that the right seat person is doing are not inherently required to be there. And if they're not there, the pilot can still efficiently use their systems with just that left seat pilot is really important to the design, the decisions that we've made and really influenced a lot of the flight deck architecture. Because we wanted to make sure that if we're building a new aircraft and someone's buying a brand new aircraft, it doesn't feel like it was designed 20 years ago. And it doesn't feel like you need that second pilot there, even if they're not required. You really would love to have them. And those kind of conversations were really common in the early days and continue to be had as we make kind of design decisions and trades on what we're going to have or not have in the flight deck. And I think that's really come out of Beta's culture of really just flying everything as much as you can to get familiar with those kind of compromises.
Cool, thank you. Any more questions from anybody in the audience?
I wanted to ask about performance-based certification. If you could explain again, what is the difference between performance-based and non-performance-based?
Yeah, so it just at its core just brings a lot of the regulations and the requirements that you have to meet kind of up a level. So instead of saying the, display must show X, it just says that the display must be provided. So like, for an example here, this talks about a takeoff warning system. So this is showing that there must be a takeoff warning system provided. And so that is the requirement that you must meet. And historically, a requirement like that would be in the regulations. Now, kind of taking that step up and that step back, the newer rules say that information concerning an unsafe system must be provided in a timely manner. So this allows us as the OEM and the aircraft manufacturer to kind of mold our certification basis around the systems that are incorporated in our aircraft. So historically, with piston and fuel gauging aircraft, there are very specific written out requirements in the previous amendments of the rules. And now, because we don't comply with those and we don't have to comply with those because we are an electric aircraft, coming up to this Amendment 64, where it's performance-based and more of that safety objective, we can better choose regulations and requirements that actually fit our aircraft. So this really opens the door to a lot of innovative designs that historically wouldn't meet the regulations. However, they do meet the intent. And so this is just bringing forward the intent of the regulations and the safety considerations to create a compliant aircraft. So I like to think of it as just, it's instead of being really specific, it just takes it that higher level so that you meet the intent of the rule without having to abide by the very prescriptive requirements, and you can mold it a little better.
All right, and then for your compliance finding, what form would that take? Is it some kind of system description? Says, oh yeah, our design respect that
Yep. So
intention of the performance.
Yeah, so the FAA will accept the DDSs, which I think this slide explains it a little bit better. So those prescriptive requirements, instead of being outlined by the Part 23 rules, they are now in technical standards or using those rules. So the FAA still has to approve in the certification basis and certification plans what specific prescriptive requirements you're following. And then once those, which are called DDSs, once those are accepted, the means of compliance or the methods of compliance are the same. So you do, like you're saying, the systems descriptions or various analyses, safety assessments, simulator testing, flight testing, and all of that. So the compliance package at the end of the programs look identical to how they did before, except the requirements that you're meeting are structured in a little bit of a different way.
Okay, so the DDS is the new layer in between what would have been the certification requirement and your standard of certification plan, or?
Yeah,
Yeah.
it really allows us to be more bottom up. The manufacturer defines how they achieve the same safety outcome that the rule was originally intended to drive. And so in a traditional piston aircraft, manifold pressure, you've got to have it, you've got to show it in the primary field of view. And we go, hey, we have an electric aircraft, we don't have manifold pressure, but we are a single engine, equivalent to a single engine piston that you probably certify under Part 23. Instead of having to go back and forth on why we don't need to show that or why we have to have now a manifold pressure that's like made up and not real and doesn't make any sense and it's hard to train, we can go, hey, we don't have that, but we're going to propose a means of compliance to show a different engine parameter that shows the health and status of the engine's function, that provides the same safety outcome of the pilot knowing the status of their system. And then the FAA works with us to go back and forth and then ultimately hopefully accept our proposed DDS standard. Obviously, that's often informed by an industry consensus. So if there are things already that not just us as the individual manufacturer, but other electric aircraft manufacturers have agreed on as the way to achieve that safety outcome, then that's often the case, which is where some of the ASTMs and other things out there come in. But I think that's the benefit to us and to the FAA is it also reduces a lot of the churn then where they're trying to apply prescriptive rules that really don't make sense for our aircraft design, knowing that they're not going to be able to expect us to meet them.
All right, and just last question. So I'm new to the DDS. So is there a DDS document that exists, or you need to come up with it and have FAA agrees?
A little bit of both. The FAA has what they call noticed DDSs, which are pre-approved prescriptive requirements for each regulation. If outside of that, you can also propose separate DDSs to that. So a little bit of both.
All right, cool. Thanks.
Thank you, Phil, and thank you guys for giving this explanation. What I like to with these webinars as well is try to provide as much information to folks who are early in their career and want to understand the different parts of human factors in aerospace. And I feel like all these details of certification are sometimes things that you don't really learn in school and that you have to kind of learn on the job. And it's nice to have kind of people who can explain these kinds of things and give that information to folks. That's one thing that I like to ask as well towards the end of each of these webinars is if there are folks watching in here who are students or who are early in their career and looking to get into this subject area or this part of HF and aerospace, what do you recommend? What do you think is a good first step for folks who are interested in this kind of work?
I'm looking at you, Tyler.
I know, I'm thinking. I got into kind of flight deck design and working for an OEM straight out of my college. I was at the Boeing company prior to here at Beta. I kind of knew that I wanted to get into flight deck design and pilot interface. So I put a lot of my efforts toward understanding I'm a pilot, so learning to fly was one aspect of it, and also what companies are out there and what are they doing to kind of break the mold, and how to get into that, because I knew that I wanted to work for an OEM, so I'm probably not the perfect person to answer this question, but attending things like this and understanding what the differences are between all the different aspects and facets of human factors and how you can integrate. It's a lot bigger field than I think I initially understood, because I was so laser focused on going to an aerospace manufacturer. But there's a lot of other facets to it as well, and kind of understanding where your niche is was exciting. And then kind of understanding what, like Rodrigo said, certification, to me, I didn't learn anything about it until I was in industry. And it was quite an uphill battle to get into it. But now that I kind of have that baseline understanding, it is pretty similar across industry and across the different places that you'll go, and the concepts are very much parallels. So
Can I reflect that question back to the audience?
Yeah.
So Josh or Tom, if you're still on, I'd be curious if you could talk a little bit about like operational suitability and flight standardization boards, and what kind of like things will be publicly viewable and digestible by the people who are on this call as we start to certify vehicles through the AED.
Yeah, sure. I can speak to that for just a second. So that's operational suitability is different than airworthiness criteria and certification. So basically, the Flight Standardization Board or operational suitability determination comes towards the end of type certification for an aircraft. And FSBs are typically, or flight standardization boards, are the process in which a type rating training program is designated as operationally suitable, and the type rating is established at the end of the board. And that typically comes towards the end of the type certification process. And the result of those are what's called a Flight Standardization Board report, which is essentially the baseline training programs for Part 121 or 135 operators, and those are published in the dynamic regulatory system. And operational suitability report is basically the same process, slightly abbreviated for non-type rated airplanes, or aircraft, or modifications to aircraft. And those are also published on the dynamic regulatory system. It's kind of a baseline for operators and principal operations inspectors for the FAA to design training programs. So I think that answered your question, Tyler. I hope it did. And Thomas Good is on the line here too. He'd feel free to add anything that I missed, Thomas.
That answers my question. Go ahead, Thomas.
I think Josh hit it. The only thing I'd add is that this is going to be a very interesting new field that's coming around, where it'll be curious to see how training evolves post certification. So me and Josh have talked about, is there going to be a need for training for pilots converting from electric going to piston or gas-based aircraft 5, 10, 15 years down the road, when the majority of the aircraft are now electric versus having a gas-based aircraft? We're thinking similar along the lines of conventional gear versus tricycle gear. So we're kind of thinking ahead and seeing what's going to be coming there, and we're excited to see what's coming. So
Cool. All right. Anything else to add from any of our speakers? All right. I think we'll end it here then. Thank you all for participating in this today. Thanks to everybody who joined the webinar virtually as well. Like I said, if any of you are interested in participating in one of these webinars in the future or know anybody, please reach out to me. And hopefully we'll have another one of these with another good group of people in the next month or two. So thanks, everybody.
Great job.